Alright, so we're back, and this time we are looking at the calculation of the relative stuffs from 2 to 1. And you would realize that 2 is a Schuppe link. So we have to use the formula for this one. So formulas for R, V, and omega are right here. Now, let's take a look at some of them. So R1, 1, 2, this one is just copied from the formula, but it's important to know at least what A1 is. And in this case, A1 is the distance between the two z-axes. And this is axis 1, this is axis z2, z1, and the distance between those is the A1, which we know immediately. It's actually this distance, A1. And no matter what the rotation of this thing is, it's still A1. So this distance is A1, period. Dot. Now, where is alpha 1? Right? Alpha 1 is the rotation angle between the two z-axes. Right? And in this case, it would be rotating from 2 to 1. No, actually, alpha 1. Hold on a minute. Yes, alpha 1. Is that correct? Yes, it is correct. So alpha 1 is the rotation from 1 to 2, I think, and it's in this direction. Yes, that's actually correct. And let's make the assumption that this from Z1 to Z2 is actually 90 degrees, like it's shown on the graphic here, so that alpha 1 is 90 degrees, and I'm going to check the signs right now. So this rotation axis is actually negative 90 degrees, because we have to follow the right hand rule for x1, and that if you follow that, you find that this rotation is actually in the negative direction. So it's actually negative 90 degrees. So that gives us the coordinate of negative q2 and this one, cosine of alpha 1, that's going to be 0. So the z, so that's just as a sanity check, in the z direction of 1, the coordinate of the second axis is 0. So it doesn't move in the z direction of 1. In the x direction, it's a1, which also makes sense. And in the y direction, it's negative q2. So q2 is this one. Actually, it's q2 because alpha 1 is negative 90. So negative 90, and so sine of negative 90 is actually negative 1, and that combines with the negative sign here to come out to be positive. And so the y coordinate of the axis 2 is actually evaluates to q2, which makes perfect sense because this is actually q2. which I think also has the other name, and that is D2. So Q2 is equal to D2. Okay, very good. Let's provide a little more explanations, because these are the formulas, but let's see, to see the intuition behind the formula, we have to actually see what it actually looks like on the graphic. Let's return to this formula for a little while, because we haven't explained that in the last video. But basically, this one is telling us to take the cross product of the 2's angular velocity and where 3 is in relative to 2, and that should give us the velocity of 3 relative to 2 in 2's frame. That's a very mouthful, but the angular velocity of 2 in this case is actually 0. Why? It's a little complicated. Actually, the angular velocity of 2 in 2's frame is not 0. Let me show you why. The reason is that the angular velocity of 2, which is this one, could also be influenced by 1. Right? So let's say 1 rotates in this direction, and it takes 2 with it, so 2 actually also rotates in sort of that kind of arc. So if you imagine that rotates around, then 2 actually rotates around in kind of arc like this. And so this vector is actually not 0. Oops. And the R2, 2, 3, so this vector is also not 0. And it's also, so this cross product, it evaluates out to something that is not 0. And well, you might say, wait a minute, does that make any sense that's not 0? Because I can see here that the 2, so the coordinate system 2, and the coordinate system 3, well, they never move relative to each other. They never translate relative to each other. So where is this velocity, this non-zero velocity, coming from? And that is a very common misconception, because this velocity is not what 2 and 3 observe each other to move in their respective frames. This velocity is their relative velocity, not as they themselves, or not as 2 and 3 themselves actually see each other moving, but it's just only the difference in their velocity in the inertial frame translated into 2. To see the intuition, and this graphic is a little hard to follow, but this is an example that highlights that fact. So this is a trivial one that says, let's see here, this is 2 and this is 3, and we imagine this segment is fixed, right? And this segment is also fixed, right? And this is actually an axis that rotates like so, right? So in 2's frame, which looks like this, the coordinate system 3 is not moving. right? The R2 to 3 is constant, which is 100% correct. Now R2 3 2 dot is 0, and this dot signifies that I am taking this thing and do an d over dt over it, right? And if I actually do that, then that would come out 0. When would it be not 0? Well, it would be non-zero when, for example, the 3 actually extends out to here. Then that R23 dot would be non-zero. But in this case, we are assuming that it is. However, this is not V223, right? And this is highlighted in the lectures already. Why? Because in this derivative, we are taking the derivative in frame 2. And frame 2, since it's rotating, right? See, it's rotating because of this one. It's not an inertial observer, and so we're not. So it would be wrong to write the V to conclude that this is its V. So, well, let's say this is L1, and the longer one is L2. Actually, let's change that to L3 to see it a little more easier. This is L1. Oh, L2 actually, I mean L2. L2, right? So what is V223 in this case? Well, for that we have to translate everything into the inertial frame, right? And in the inertial frame, let's say everything is rotating with some angular velocity omega. Yeah? Then V223 is going to be, I'm just going to write out, L3 omega negative L2 omega and now I actually translate into frame 2, which is still the same, pretty much. And so, because this multiplication actually calculates the change in position of 3 and 2 in the inertial frame. And this comes out to be something non-zero. Alright? And if you rewrite it a little bit, you would find that it's actually nothing different than L3 negative L2 crossed with omega. Yeah, also, so omega. And actually omega 2 or omega 3, it's not that different. But it's actually, in this case, just like the omega. And this one is nothing different than R32 written in 2's coordinate frame multiplied by 2, the rotation velocity of 2 in 2's coordinate frame. And it comes out to be non-zero. And this number just means that since 3 is further away, it's moving faster, right? And 2 is closer, so it's moving a little slower. And it's this difference right? This difference vector, this green vector, that is the difference between that and that. And remember, these two blue things are in the inertial frame. So this green vector is actually v32. And if I write this green vector in coordinate system 2, then that is the true like v32 in 2's frame, which comes out to be non-zero, which is completely different from this one. And basically this dumbed down example should give us the intuition for the example above. So in the above thing, this thing is not zero, because, and why is it not zero? Well, because the 2 here is, the 2 is here, 3 is here, but look, 3, and when the z1 rotates, well, 2 and 3 rotates with it at the same angular velocity pretty much. That is provided that that this thing doesn't change too much. But since the 3 is further away, its velocity is actually a little larger, so it rotates a little faster. It moves a little faster, and this is why this thing comes out to be non-zero.